So let me recall briefly what my yesterday's talk. So we start with a reductive group over a globe on fin F. So for time being, I assume G to be split. And so the duon group, G hat, is Lana's duon groups, connected reductive group of complex numbers. And G fixed irreducible representation of G hat. Okay, so now for let Fv be a local non-Archimedean field, a compression of F at some place. So let me summarize the Braverman-Kasdan proposal of generalizing Gottman-Jacquet story. So we want so you want a Rorschach space so the existence of Rorschach space S rho of G of Fv, some vector space of the function on GFV that are locally constant function on GFV, but not compact support. They are going to have compact support in some partial completion of G. So for instance, when G, in the standard case, when G con G and len, Rho's net representation, this is space of locally constant function with compact support in space of matrices, right? So this is the first ingredient. And the second ingredient is the basic functions. So this is, I mean, it's not exactly in Braverman-Kasdan conjecture, but that's the way I try to reformulate things. So we have the basic functions. That can be beta rho of V inside this space. So this function, so in the case of standard case, this is just a characteristic function of integral matrices, right? And it has a property that when the trace on irreducible representation would be the L factors if the representation is unramified and zero otherwise. So is L factors at some spatial point. So let S naught. So S naught is something like a negative of nu G. Nu G is half of sum of positive roots against lambda of rho. Lambda of rho is dominant weight of rho. A pi, if pi is unramified, and zero otherwise. And three, it should have the Fourier transforms, so the rho Fourier transforms. On this Schwarz space. So it had to be of the form, of the form so phi is a function in this, so this is an element S rho, and you want it to be some Bessel canons conform with phi check, and phi check is of G is just phi of G minus 1, right?
Could I interrupt?
Yes.
You must have said what the Rho-Schwarz space was, but I didn't hear the Rho. What do you mean by Rho-Schwarz?
So that is a conjectural vector space. That's supposed to generalize the space of favorite space of Jacquet, the space of locally constant function composed upon the in space of matrices. But you view it as a function on G. So that means a locally constant on G, not with compact support, but it becomes compact support when you add some boundary to G. But then on the boundary, in the case of matrices, the space is smooth. So you just take this smooth function on. In general, it's going not to be smooth, so you have to put some asymptotic conditions. That is still mysterious. Don't know how to do it.
There is a formula due to the Ford which specifies this in terms of a functional formula. It's rather mysterious also.
Well, yes, assuming that you know the L factors, local L factors.
Yes.
Yeah. So, but in general, you don't know the L factors, but So you want that what you desire is when you let the function this Schwarz space act on representations, then multiply by inverse of L function, you get some regular functions on the space of representations, right? So in other words, the acting on metric coefficient, it can be the denominators is given by L functions.
He doesn't need any root numbers, does he, for the Fourier transform? I think he does.
No, for the space, you don't need the root numbers.
Fourier transform.
For the Fourier transform, yes, maybe, but I'm not going to. I think you really need to try to build things on geometric side, and what he does is, he tries to assume the spectral side and go back. I'm not sure how useful it is, but I mean, it gives the definition in some case, right?
This Fourier transform does space to itself?
Yes. No, that's the point. I'm always confused. Sorry, I'm not working, but sometimes it should be to row do. I'm not. No. I think no. It's G minus 1. Then it's go to S rho to itself. It's go map to pi to the contravariant pi, and rho keep the same. Yes. So if you do without this, then you have to go to rho to the do on rho. Yes. Okay. And the properties is if you want that. So in rho is standard representation, then J rho is just given by psi the trace of G, try that G to the n. So that is just write how the Fourier transform acts, and this is the kernel of the Fourier transform. You will write it in as multiplicative convolution. Right, in this. And this is just the difference between the additive and multiplicative measure. Okay, so what you want about this J rho, spectrally, is if F is just ignore on the convergence problem. If F is a metric coefficient, a pi, then this is J rho convolved with F. It should act by scalar or metric coefficient, and this should be the gamma pi of F. So gamma factor rho, gamma factor of pi, right? So this should act, on metric coefficient. It should multiply by some factors, and what is important is this factor gamma should depend only on the infinitesimal character of pi, not on pi itself, right?
Say that again.
So the gamma factor should depend only on the infinitesimal characters of pi, not on pi. So in the same induction, to have the same.
So for example, if the Steinberg and the trivial.
Yeah. So that is different with L function. The L function make pick this different value, but gamma factors. So I mean, so yeah, okay.
So in
Yes.
the story you have first chosen a fixed additive character.
Yeah, I had to choose psi somewhere. Yes, yes. And the last things, okay, may I put it here so I don't have to erase. That is, the 4 is some kind of a Poisson formula. That is some f with some under local conditions. So now with this local Schwarz space and with the basic function, you can form the Schwarz space identically. So S rho of G of A would be function of the form Fv, any Fv in the local Schwarz space for finitely many V. But in other place, you want to pick the basic function. Right, and then put in some limit, and that is inductive limit, and you want to prove that. So this is important, but I have to put it in the corner because I don't want to erase this blackboard. You want that the so you have this J, and then you want that the so that let me call this the Fourier transform rho of phi. Then you want the sum of G in G of F of phi of G is the same as sum over G in G of F of the Fourier transform phi of G. So here somehow we ignore on the possible point of boundaries, right? And then you need to put some kind of local conditions on these functions. So otherwise, I don't know how to form.
So I understand, because for the matrix algebra, it's a sum over matrix algebra.
Yes, but you will put some local conditions, so just everything on the boundary is going to be 0. Yeah. Okay. So we know little about this, but we do know a couple of small things. To
Just repeat the definition of the global Schwarz space.
so precisely you look at the finite tensor product over some finite place of S, and then you make inductive limit,
Yes.
but with the help of these basic vectors.
So almost everywhere it's the basic vector.
Yes.
This Poisson summation is a conjecture,
All this is conjectures.
but that's sort of different level.
It's different levels.
I mean,
Okay.
do you have any example
No, they-
other than matrix?
No, but I am discussing why you. No, I mean you come back to that. Yeah. Okay. Okay. So now what we know so far. So first of all, we have this. This space of Schwarz space supposed to be space of function on something, right? And then definitely you do know it is the so for every you have this M rho called the reductive monoid. So this is so it G contains G, and G up on the left, on the right, over rho, right? So by the way, I should only put myself in this better situation where G have a GM, and here the GM, the C star, act as C star on this. So just make things better. I mean, you can only do that just by adding formally some C star in your group. So it's kind of harmless things. Okay, so you can construct this by the following procedure. So if any reductive monoid, so it's a irreducible normal of phi algebraic varieties containing G, with G acting on the left and the right, and then when you look at the maximal torus and look at its closure, then you have not a toric varieties, right? And the toric variety is defined by some cones. So some cone sigma inside this, the space of characters, and it just can and this cone has to be invalid under action W, right? And not just one cone, because it's a phi. It's a phi. Yes. And yeah, that's why, I mean, usually it doesn't seem that it doesn't exist. When T is simple and W, going to move it around. But with the GM function, you can make it. Because of the GM, you can you can make some cone like this. You know, and this is the weight of rho, and this weight of sim2 rho, and so on, and that makes you a cone. And so, you know, irreducible representation of dual group will give rise to the simplest reductive monoid. And okay. And of course, when the standard representation, you just got like a space of matrices, and that is basically the only case where this monoid is smooth, is regular, and then usually it only says singularities. Okay, so and what is, I'm not going to say precisely, but this theory is very well built. So there is kind of functional realities. You can map one monoid to another, and that is a way that there should be a way to have a resolution of singularities. Of M rho, just by using the monoid. You know, the monoid is, you think about the so-called the universal monoid, is the one when you map G into on the fundamental representation of G, and the monoid is just built by and adding on the GM factors, and built by taking the closure of that, right? And if you remove the zero in the space of endomorphism of the of this fundamental representation, then it becomes smooth. So all non-smoothness come from zero. So in order to solve it, you have to blow up zero one by one, and the blow up by zero actually just can be encoded in this theory of monoid. So it worked very well in GN2. In general case, then I don't know how the order to blow ups, and I get confused. But in GN2, it doesn't. It looked quite pretty. So we can hope that you can see that maybe this Schwarz space should be just a space of locally constant function on that resolution. That's what the naive hope is. So this maybe give rise to the S rho would be. So that is the one of the first naive hope I can get.
Right. You hope that it's locally constant on some nice resolution.
Yes, on some canonical resolutions. Yeah. Yes. And the second is, now we do understand it. Now this kind of solved questions. So this is given by the basic functions, even by the choice, quotidic choice dictionary, by the IC interaction complex on the formal arc space of M rho.
Sorry, what was one there?
So this is one.
What is
So
the
the-
resolution of singularity?
Yes, yes. So I'm just saying that first of all, you can construct a monoid. So on this function should be function on the monoid, right, with some mysterious condition boundaries that should correspond to Beam-Casterman calculation somehow.
So you can resolve the toric variety and know how to resolve. Right?
Yeah, toric variety can solve it.
So somehow you construct your resolution from the one of the toric variety.
Maybe. No, but the way I can solve it not that way, by just using on the map I get from monoid and try to glue them together in some. I mean, in GN2K there's only the graph is just one directional, so it's very easy to glue. In general, I have some crazy graph. I have no idea how to glue. Okay, so okay. Well, so this in this case, you have the you know the basic functions.
So you mean the resolution is small also?
Oh, I'm not.
Or,
I don't know. Yeah, maybe it's more. I haven't
is the
calculated.
basic function supposed to be I mean, on the loop space, I mean, so you say it corresponds to the intersection complex.
No, but it's not. You know, there is this relation to the M row, but now we have to go to arc space, and it.
Yeah,
I don't know how. Yeah.
because I don't know, I see an intersection complex, you're talking about the resolution, so I'm wondering if
Yeah.
it's just the edge of the complex.
Yes, but I think the point of the resolution will see more than just the IC, right? Because no, I mean maybe talk a bit later. Yes.
I didn't know that this is the correct basic function to take.
So because when I take the IC, it act on the L function, then it satisfies what I want.
It's a
Satisfies property 2.
Yes, yes.
You should mention that you get these Poincare polynomials, that's what the basic function is.
Uh huh.
You haven't given a picture somehow. Yeah, okay. It's
Did I?
the basic function is at each point of the cone, the basic function is a polynomial in Q.
Yes, sir. That's right. That's right. Yes, that's right.
It just happens that for GLN it's 1. And
Yes,
standard
that's right.
representation It's just 1, but in general it's a polynomial in Q.
That's right. Okay. Okay. Now I want to focus about the 3 and the 4, mainly the 3. So we don't know what is this Fourier transform, but we do. I think we have pretty good idea of what it is. Especially you really understand in the case of finite fins. So in the case of for finite fin, for reductive group. Okay, so let me make an assumption. I mean, it's severe assumption, but you don't need it for the finite field, but it just makes everything simpler. So let's assume that rho is multiplicity free. So when you restrict to the maximum torus, you have the weight dimension 1. So that works for GN2, of course.
So you mean the restriction to the torus is multiplicity.
Yes, the weight, multiplicity 1. So I mean, I think we don't really need it, but it just create an extra
That's very rare.
a minuscule for. I think in the case of GN, we can solve this problem multiplicity in the case of finite fins, but it just create extra difficulties. I don't want to go too many difficulties together. So how the gamma factor is constructed? This is this is constructed proposed by Bavman and Kasdan. Okay, so we have the G hat going to G and V rho. Okay, then you restrict it to T hat. And now because of the multiplicity free, we have a canonical map into C star to the R, right? And now do only you have so this is rho, this go on this rho T, and so do only we have the map from GM to the R map to T. This is the do one of rho T, right? And now over GM to this kind of standard torus, you just put what you expect to be the Besson factor, you just exponential. This is the sum to the additive group. And we just decide that we have some. So now I'm working an analytic shift over the reductive over finite fin. So I'm going to construct this function J as a shift, as some elliptic shift over a group of finite things. So that's the way that I'm going to proceed. I will pull back psi of psi. So psi is additive characters. And pull back to this and just push it forward. So for example, if T is GM, then it is a constant shift that Pierre construct in SJ4.5, right? And this so basically is kind of very general like constant shift. So what is very nice actually with usually with this condition of with this control with the C star, one can prove this is actually a local system. This local system, line constant shift. And so what is so
I'm sorry, I don't understand your notation. What is rho hat T something? Oh, that's up a shriek.
So upper shriek. So I pull back the function to this, and I just integration the fiber to T, right? So, right. And now, in order to do I want to do the induction to. So for that, what I need is to have the W accent. So this is called phi of rho. Right. So here I do have W accent, and here I have the accent of the symmetric group, right? So, but the point that with the accent of multiplicity free, if you can actually have a map from W to this, and so they do give you a W accent. So it's obvious with multiplicity free. Assumption. So in general, you can construct a canonical W action, but it's more subtle. So you need to fight against these ambiguities of weight. But it's possible. It's just basically again due to the fact that the Haas-Davenport identities on Kosterman sum. So there is when you switch variables, it does change psi, but just change by -1 we know. So you just twist by that psi and so on, and then you get something that is canonical. But that is not. And so with this, you can build. With this, you can build a G equivalent perverse shift on G. That should correspond to the. So let's call this phi of G of rho. Maybe it's called phi T of rho. Okay, so so you it pushes back and then it pushes forward to G and then take W invariant. But it's not induction, but W induction should be just do this, but then it because with W action. So let me write the formula. So it's P is Q, and then this phi G is so you have your shift on T, you pull back to the Hodelic resolution, G-Tinder, and then you push it forward. And then you use the W equivalent to take the W invariant part. Okay, so they basically you need to know that this give you the right answer. That means this kernel, when you act on metric coefficient, that should give you the right gamma factors, and that is something to be proven. It's non-trivial. It's called the conjecture of Bergman-Kasdan conjectures 9.5 in their first papers, and so they prove this for G semi-simple rank 1. So for GN2, and my student and myself prove it for GN len and every row. So that give you the so this give you very so that you're confident that this is the right construction.
Could you just say what the conjecture was again? Or
So it's just like here, you want the basic thing you want to about gamma factors is that it depends on the infinite character. It preserves induction, right? And so you want that this kernel also preserve induction. And translate into function in terms of shift that gives some formulas. I don't remember the exact formula. Had to prove something, some vanishing things. Yes. Okay, and now I mean this concept is kind of mysterious. You don't know, but intuitively what you can say is actually it's not so hard. When T is split torus, right? You just do the integration along fibers from the sum of exponential, right? So when for element T is not split torus, you just have to twist things. You twist the T, twist the GM, and do the same operation for untwist torus, right? That was for the regular element. So regular element, that is what you do. So for if you split, you just look at this. If non-split, you just take another torus, and then for the singular element, it's just obtained by these intermediate functors. I mean, it's crazy functor. I don't know what it is, but it does seem to work in this case, right? Okay, so that's what I'm saying about the finite fins. So how about the periodic fins? So periodic fin is, at least for multiplicity, it works exactly the same way, right? You have this map, right? And with this multiplicity free, for every twisting, you can twist compatibly, I mean, canonically the GM. And so you can push, now it's no longer analytic shift, but just some function, it's just integration of fibers. Of course, this is not compact, so you need some regularization. But it does well, it's not a trouble. So, in the periodic case, you can have the same construction. With function instead of analytic shift, right? So by this process, we do get a function phi G rho from G regular semi-simple to C, right? Just by if you split and you look at the integral in split case, with non-split and look at the other integrals, it looks a bit weird, but that's what happened in the finite case. The whole point how to glue them together, so that you have to prove something. So here the missing point, you look at this middle extension. But in the periodic case, maybe you don't even need that, because the missing point is a set of measures 0. So you just expect that this thing conjectures is this is your local integral function. And that gives you a distribution on your yes.
Sorry, what do you do for a non-split torus? I didn't understand what.
Okay, so when the non-split torus you obtain from the splitter by twisting by W, right? in this, with the assumption multiplicity free, I can have this canonical map. And then so I can twist, using the same twist with this GM to the n, and get some kind of extension of the fins. And then I can do the same integration with the cause some regularization, but it doesn't. It's not a big deal. And so now the conjectures. It's completely well formulated conjecture. This is locally integrable function. So you just define your function on the regular semi-simple element of different tori, right? And it lies in Harshon's theorem on characters. You want it to be a locally integrable function, and you want this to be so that's what I call J rho here. Maybe you have J rho has to twist by some power, some determinant. There's some discrepancy between the determinant in G and the torus. I haven't. So you want that that this thing is map of phi is J. So let's call J rho is phi rho times some determinant factor that undetermined, that need to be precise. Then this Fourier transform is J rho which phi check map S rho into itself. And the third conjecture is this thing is the basic function. It should stabilize basic function. Okay. So I mean, there one case even I haven't worked it out, but I think it just doesn't seem to have any difficulties. It's Newton torus, right? And Newton torus, you don't have the first statement is obvious. You don't have to do anything.
The second statement, the Fourier transform statement seems trickier.
No. That is what. No. Integrated torus has no problem. This is a Hankel transform. Right? The Hankel transform usually you have some kind of vector space and kind of circle action, and look at the quotient from the transforms under the circle action in some way, and this is what you have here. So you have GM. So this is where the toric variety appears again inside AR, and this map to T, and this map to the toric varieties, right? So so here is some kernel, some S, some subtorus, some multiplicative subgroup of the kernel of this, and you just look at the co-invariant space, the function on AR co-invariant. Look as a function on MT. That is your Schwarz space, and the Fourier transform act on the co-invariant subspace, and it acts. I mean, I haven't worked out the detail, but I don't think there's any problem.
The issue, like in ordinary Poisson summation, Schwarz class going to Schwarz class is not so much. Usually, you make the first function very smooth and rapidly decreasing. If you have singularities at infinity, one is very nervous that the
everything you do is on the level of the smooth things. And math going from T is just some co-invariance process. Yes. And by the way, in this case also, the Poisson summation should be obvious. It's just like Voronoi formula. Right? The Voronoi formula. So for T, I think for T it's not work out, but this is Hankel. That's my title, Hankel transforms. And the Poisson summation seems to be a generalization of the Voronoi. Yes, that means that when you have a plane and the group S is a circle action, right? But you can just, you do the Poisson summation on the vector space and integrate on your torus, and then you get your Voronoi formula.
And that's very close to the ordinary one.
Sorry?
It's very close to the ordinary one.
It is ordinary one, but it just, I mean, it's just, I wonder why nobody did it for, other than for the for the Gauss integers or something. It should be work for any number of things. Okay. So now I have 5 minutes, right? Do I?
Sure, that's
Okay. So now, so that is about the number 3, right? So you see, even we do have some way to try to approach this number 3 problem. It's not as desperate as we thought. Now, how about the number 4? Poisson summation. Here, by the way, I think the effort that I made is really try to get a local statement that would imply the global information we need. So
one thing in terms of what you said yesterday concerning exactly this point is you said that if you integrate, then you'll have the identity.
that one.
You have a strong belief that the identity holds point by point. In other words, you're asking for something
So let me
potentially stronger.
let me discuss about this now. But I'm just saying that the whole general point is that the implication from local to global should be taken care by the choice formula. So you need to set up in the way that the choice formula will reduce it from global desire to some local identity. So that's what I try to. Right now I don't. So let me just say what I do. Okay. So Bachmann-Kasdan conjecture that these things, right? Sum of phi over g is the sum of a rational g, the sum of the Fourier transforms. So this is, for me, pretty desperate as the thing to prove. But if you integrate and have much better shape, so we can integrate over, how do we say it? So if you put x minus 1x here, x minus 1x here, and then integrate on x variable, right? And then you have this GA mod GF, or whatever it is here, of the Bachmann-Kasdan Poisson conjectures, right? So by doing so, we just get the choice formula for. So on this side is the choice formula. So we just get the sum over gamma in GF tilde of operagon of f. But now f is no longer the usual space of function, but f had to be in this Schwarz space of rho. So what you want is something roughly like this. How do you call this best Fourier transform rho? So in the spectrum side, that would be a sum of L function equal to the sum of dual L function. So this, I mean, of course, so how can you go about this? So the first naive idea, why don't you just put, because this thing into tori. So let ignore singular element and put thing into sum of tori, maximum tori, and then maybe gamma in T of f. Now we have some repetitions. but just ignore it. And so the first naive guess, you can just erase this. This may be just equal torus by torus, right? 1 second, don't be set. It's not true. I know that it's not true. I made enough conclusion. It's not true, but so. Sorry. I had to fire in Peter, skeptics. So this would be true. If this guy, the operantagon functions, so let write this as a function on gamma of, so if, okay, so how do you write this? So if the, so let me call this, like look more like a function, so theta, no, I get confused. So I'm just saying that the function gamma map to operand gamma of the Fourier transform rho of f is the Fourier transform rho on T of gamma map to O gamma f. So this one, you apply the rho Fourier transform on the torus. If you get this one, then it will be done. That is your Hankel transforms. So this is a kind of local identity that we may want to get. So I said that this is wrong, but it actually says some element of truth in it. So why I'm saying so? Let's say in case of, I think it's true for split torus. For split torus, something is very nice happens. So for instance, you can safely ignore on just look at the basic function because almost every is a basic function. What you want to compute is a basic function, right? So for split torus, what is ultimately true? It's surprising me. I don't even have a conceptual proof of it just by calculation. When you look at the basic function of G rho and do the operantagon gamma, when gamma is the split torus, and then you get up exactly you get exactly this.
So what is?
This is the basic function in the torus, and that given by your favorite partition function. So this is a function on T of f to C star. And of course, because you have this weight lambda 1, lambda n, this I just try multiplicity free, right? And then this function is just any mu inside this, so p of mu. I want to map into the number of how to write mu as n1 lambda 1 plus nr lambda r, right? Yeah, so this is exactly how symmetric powers works, and it's exactly the IC of the toric variety of the formula of IC varieties. Okay, so it's not so wrong. It's something is true, right? So now more serious test. Now it's when it fails miserably is when you look at. So by the way, we have very limited data to calculate. So this is the one data that you can calculate. The other data is now led back to the K of G equal to Gn2 and standard representation. Of course, this is, for L function, everything is known with many different ways. But let's just try this, maybe this stupid approach.
It's known by?
No, for Gn2 standard representation, you know the L function, the Hankel L function, it has functional equation. There's nothing new to be proven.
I guess what you're giving is a trace formula proof of the analytic.
Yes, yes. So what you would guess is somehow on the spectral side functional equation, on the geometric side would be the Poisson summation for quadratic extension. That is the basic idea. But in this case, this local expectancy is wrong. So this is that in lemma 1 in bioendoscopy Langland's papers, he confused on this open integrals. In bioendoscopy papers, lemma 1. So when you do the phi is you start with the function phi is a characteristic function of Gn2 of O. So this is something very funny that happened. So I just take 2 minutes to write things down. So let's look at the quadratic, some t correspond to some quadratic extension. And when you compute, so all the split torus, it just give you the characteristic function of Gn or t. In the split, nothing happened. It's just this, and this is just constant function. On the non-split torus, so you have something like this. You get something like this. So the orbital integral of gamma is in E star, will be as a function. Just let me write as a function. Is a characteristic function of O star plus F1 plus F2 plus F3 plus etc. So this is not smooth function that we expect, right? Because it has often have singularities and because it's infinite sum. But Fi is a characteristic function of something like this. So I mean I got confused with E, but let's try with split torus. That would be x and y in O, and x minus y is in P and O, right? So this is a discriminant, right? The eigenvalues is closed, right? And Fn would be the characteristic function of the place where x and y are in O, but the difference is divisible by p to the n. And this function is not autodual, right? Because this is not this compact support but not smooth. When you do Fourier transform, you have something that is no longer compact support, right? but smooth. But the point is that if you do the Fourier transform of this, you get this function. The Fourier transform of this, you get, if you're not mistaken, you get x minus y is in O, but x and y is in P minus n O. This function, right? So it's almost the same. We just have some kind of scaling factors, using your homothesis. So the fact that this function is not stable by Fourier transform because some factors. H1 is almost autodual, but up to these scaling factors. So maybe I hope that this is a general feature that this open is not autodual, but you can decompose it into pieces that are almost autodual. But I failed to formulate something general. Thank you for that.